Okay, YouTube, in this video I'm going to run through, hopefully get all 5 of these examples done, but through 5 examples that are very common when it comes to proving trig identities. Okay, so proving trig identities is essentially basically something that math teachers at least ask students to do a lot of the time to learn how to write complex trig statements as more simple trig statements. But the bottom line is this: when we prove trig identities, in this case, in terms of what the examples you see here are, we're basically trying to show that one side of the equation is equal to the other, and our method for doing so is working on one side at a time in order to transform it into the other one. So we tend to work on the more complicated side first. Remember, the intent is to rewrite it as a simpler statement, but to try to show that it is equal to the other side. So let's go ahead and start by taking a look at number 1 here that says cotangent x minus 1 is equal to cosine x times the quantity cosecant x minus secant x. So in order to show that these are equal, we'll go ahead and work on the right-hand side since it's more complex, but we're just going to use trig properties, so like factoring, distribution, adding, subtracting fractions. We're going to go ahead and look at maybe distributing this quantity on the right here. So we get, and forgive me for leaving out the x's here, but we get cosine cosecant, essentially, minus cosine times secant. And so using some basic trig substitutions, for example, we say cosecant is the same as 1 over sine. So we say this is cosine times now 1 over sine. 1 over sine. And this is minus cosine times 1 over cosine, which is secant. And so you'll notice a few things. You'll notice that our cosines here cancel out on the right, and we just get left with minus 1, which is good because that's what we want to show it to equal on the left. And now we need to get a cotangent on the left. And you'll notice that we're taking a cosine times a 1 over sine. Well, that multiplies out to be cosine over sine. So we have cosine over sine minus 1, but that really truly is cotangent. So we say cotangent x minus 1 equals cotangent x minus 1, QED. So that's what we wanted to show. Okay, so there we go. Example number 2. Now you'll notice here that it's the same kind of deal. I mean, we want to work with some algebraic properties, so like distribution, but we're going to work on the left side because it's the most complex of the two sides of this equation. So we say cosine squared times 1, well, that just gives us a cosine squared. And we say now we have cosine squared times tangent squared. So one thing to keep in mind is this: if tangent is the same thing as sine over cosine, we're going to do a very similar substitution here. It's just that since we have tangent squared, we're going to rewrite tangent squared as not just sine over cosine, but sine squared over cosine squared. And so you might notice here that our cosine squareds in this second term here cancel out, and we get left with cosine squared x plus sine squared x. So now it's always good to look at the other side of the equation to see what you're working towards, and we want this to get to equal to 1. And so for those of you who are very savvy with your Pythagorean identities, you'll know that cosine squared plus sine squared is, as a matter of fact, always itself equal to 1. So now we've transformed the left-hand side of this equation into 1, and we knew the right-hand side was 1. So these two expressions, left and right, are indeed equivalent. Okay, so yes, the Pythagorean identity says cosine squared plus sine squared is always 1. Let's keep that in our back pocket as we go through these last few examples here. Okay, so example number 3, we have 1 minus sine times 1 plus sine. We want to prove this equals cosine squared. So foiling this out, you'll notice first of all that this is a set of conjugate pairs. That is, they're identical except for one is minus, one's plus. So when we FOIL this, we get 1, and then we get plus sine x minus sine x, so those cancel. And then we get minus sine squared x. So 1 minus sine squared x. And we want to show this equals cosine squared x. But going back up to this Pythagorean identity here that basically said, hey, don't ever forget that cosine squared plus sine squared is 1. We know that 1 minus sine squared, essentially if we were to take the sine squared and put it on the other side, we'd get cosine squared equals 1 minus sine squared, which essentially is what we're trying to prove here. So we're saying now this left side, 1 minus sine squared, is the same thing as cosine squared, and that's what we're trying to show that the right-hand side equaled. We'll go and put our x's back in. So that one, that which was to be demonstrated. So now number 4. Now number 4 is interesting. One thing I want to point out is this. It's very convenient when dealing with things like this to recognize that it's a difference of two squares. And now remember from algebra that a difference of two squares, that is something squared minus something squared, is equal to the conjugate pairs multiplied together, a minus b, a plus b. But we say, okay, so if I were to factor the top of this, what I end up with is essentially this. We get cosine squared in front, because cosine squared times cosine squared gives us cosine to the fourth, t. And we say plus minus, and then we say sine squared. And I realize I'm not writing the t's in there, but just for now. But we get this sine squared times sine squared to give us this sine to the fourth. And this is all over sine squared. And this is supposed to equal cotangent squared t minus 1. So now, again, recognize, please and thank you, that cosine squared plus sine squared, you can't get enough of this identity, but that just equals 1. So now what we're left with is this. We have cosine squared minus sine squared on top, and this is all over the sine squared here. Now, keeping in mind that we're working towards getting a cotangent squared, we want to get a cotangent squared, we want to get a 1 here. You might recognize that our 1 is going to come about by taking this here. We're going to split this up. I'll try to make some more room here and make a partition here. But essentially, if we were to take this now quantity, or this quotient, cosine squared minus sine squared over sine squared, and split it up into cosine squared over sine squared, not very pretty, sorry. Let's just fix that because I'm a little OCD. Sine squared. Now this is minus sine squared over sine squared. You'll notice that cosine squared over sine squared is cotangent squared, and that this is minus 1. And that's what we wanted to go to show was equal to the right-hand side. Cotangent squared minus 1 is equal to cotangent squared minus 1. Check. So now this last example is actually very similar to the last two we've done with respect to the Pythagorean identities, but you'll notice we want to get 1 plus sine theta. We want to prove that this equals cosine squared theta over 1 minus sine theta. So our method here is going to be to work a Pythagorean substitution in for cosine squared. So keep in mind, cosine squared from earlier, from prior example, was equal to 1 minus sine squared. So rewriting the right-hand side into 1 minus sine squared on top, which I have to point out is a difference of two squares, which means it's factorable. Get used to differences of two squares with Pythagorean things. We end up with this. Oops. There we go. 1 plus sine of theta, 1 minus sine of theta. So now our 1 minus sine thetas, they cancel, and what we end up with is, on the right-hand side, 1 plus sine theta, which was what we were trying to show the right-hand side was equal to in the first place. So these are 5 very, 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 very common examples of trig identities that you'll be proving. But keep in mind, out of all of the identities you used, so example number 1 up here, we used reciprocal identities, cosecants 1 over sine, and example number 2, we used the fact that tangent sine over cosine, it's a ratio identity. Out of all these identities, the ones that you want to get used to the most are the Pythagorean identities. That is, cosine squared plus sine squared is 1, and also that cosine squared is 1 minus sine squared, and that sine squared is 1 minus cosine squared, and that those factor into differences of two squares all of the time. So keep that in mind.